4.5 billion years ago was a violent and chaotic time on planet Earth. During this period, the Hadean, a Mars-sized planet called Theia, collided with our young planet. The massive impact partially ripped Earth apart and shattered Theia, fusing the planets together and ejecting so much rock into orbit that it eventually coalesced into the moon. Scientists agree that there's no way that early life could have survived such a collision. But we do know that life got its start sometime around 500 million years after this impact, not too much later in geological terms. And this is pretty incredible because while Theia was the biggest, it was just one of several big impacts around this time. For hundreds of millions of years, these large asteroids, sometimes over 1,300 kilometers in diameter, repeatedly struck the Earth with such force that they melted part of the crust and vaporized oceans. And it's difficult to imagine how life could have gotten started while Earth kept receiving planet-sized punches. Especially because the early Earth was inorganic, lacking the fundamental molecular building blocks of life. So billions of years before life evolved into chickens or eggs, it faced a similar riddle. How did the chemical ingredients for life form in the first place? It turns out that these asteroid impacts that made the Earth seem uninhabitable might have also been the secret ingredient in cooking the planet's primordial soup. We may have planet-shattering asteroids to thank for the origin of life on Earth. Before the first creatures, or first algae, or even first cells, life emerged from chemical reactions. Reactions that replicated molecules and passed on information, the precursor to genes. Now, we're not sure exactly which reactions came first, but RNA, peptides, and proteins were all likely early players. See, nucleobases are organic molecules that form the ingredients for RNA, and many scientists think that RNA was the first self-replicating molecule, and later life developed from it. Amino acids are the building blocks of peptides and proteins, which are also essential for generating many of the reactions that life depends on. But Earth didn't start with any of these pieces of the puzzle. Today, in one way or another, the building blocks of life mostly come from other life. So the catch is, the first versions of these organic molecules would need to have been made without life. How did it all get started? The first clue came in 1952, when Stanley Miller, a PhD student at the University of Chicago, had an idea. If the ingredients of life formed from the basic materials found on the early Earth, then we should be able to do the same thing by recreating those conditions in a lab. So he approached Harold-Urey, a chemistry professor who had already won a Nobel Prize and had also speculated about this sort of pre-life chemistry. At first, Urey didn't think this was a promising idea, but eventually Miller convinced him. So Miller set up in the chemistry lab, filling a large glass flask half with water and half with gas, using a mixture of methane, ammonia, and hydrogen. This created a miniature ocean and atmosphere made up of his best guess at what materials were around on the early Earth. He then added some heat and 2 sparking electrodes to simulate ancient lightning and just left it. Over the next week, the mixture in the flask turned from clear to reddish brown. When he analyzed what he'd produced, Miller found 5 amino acids that had formed in the flask, 3 of which are used to build proteins. And these weren't just a lucky few combinations. The amino acids were produced in high concentrations. Since then, modern researchers have reanalyzed specimens from a number of Miller's experiments in the 1950s with more advanced techniques, and they've found over 40 amino acids. So the Miller-Urey experiment demonstrated that a few simple bolts of lightning in the right atmosphere could organize inorganic substances into the building blocks of proteins. There was just one problem. Miller was probably wrong about what the Hadean atmosphere was made of. See, the potential mixture of gases that make up atmospheres lie on a spectrum from reducing on one end to oxidizing on the other. A reducing atmosphere has lots of gases that donate electrons to others, like hydrogen, methane, and ammonia. Reactions that form complex molecules, like those that life depends on, tend to happen more easily in a reducing atmosphere. An oxidizing atmosphere, on the other hand, has lots of gases that take electrons from others, like carbon dioxide and oxygen. And an oxidizing atmosphere can break down those crucial complex organic molecules. Since we know that oxygen wasn't around for at least another 1.5 billion years, the atmosphere couldn't have been strongly oxidizing until after life really got going. But for the formation of those early organic molecules, There's a big difference between a strongly and a weakly reducing atmosphere. And back in the 1950s, Miller thought that the ancient atmosphere was strongly reducing and filled with gases like methane and ammonia. But we've learned a lot since then. Like, sunlight breaks down methane in the atmosphere, so a methane atmosphere probably wasn't stable over a long period of time. And gases bubbling up from the mantle through volcanoes give us a clue about how the mantle would have influenced the atmosphere of the early Earth. So, most scientists now think that the early atmosphere was similar to what this combination of gases coming up from the mantle through volcanoes looks like today. This means the Hadean atmosphere was mostly carbon dioxide and nitrogen, which is only weakly reducing. This change means that the Miller-Urey experiment doesn't work out nearly as well. It's not impossible to form complex molecules in a weakly reducing atmosphere, but they just don't form as easily. And to complicate things further, a 2022 study even found that a less reducing atmosphere would have changed how electricity discharges through it. In this atmosphere, an electric field would need to be about 28% stronger to generate a lightning strike. So the spark simulating the lightning that the experiment relied on would have been less common. But Harold Urey may have actually come up with the solution to this conundrum, before he even knew it was an issue. Way back in 1952, he'd proposed that these asteroid impacts that made the Hadean so tumultuous may have temporarily changed the chemistry of the atmosphere. But their famous experiment didn't simulate asteroids. Even in the 1950s, throwing rocks at glass lab equipment was probably against workplace safety rules. It wasn't until 70 years later that a 2023 study created a model of early Earth chemistry that revealed how cosmic blows set off a series of events that changed everything. Picture a big iron asteroid hurtling through space toward a young Earth. It's around a third of the size of Pluto, so much smaller than the collision that formed the Moon, but still big enough to pack a cosmic punch. When they collide, the impact instantly vaporizes the early ocean, melts parts of Earth's crust, and scatters iron from the asteroid throughout the atmosphere. Over the next few months, that steam and iron react to form iron oxide and, importantly, hydrogen gas in the atmosphere. As things cool over time, the steam condenses and the ocean reforms. But the hydrogen gas stays in the atmosphere for longer. It reacts with nitrogen and carbon dioxide to form methane and ammonia, creating a reducing atmosphere. So thousands of years after impact, the right conditions emerge for sparks of lightning to make amino acids, just like in the Miller-Urey experiment. Even more than that, scientists have since found that sunlight passing through this atmosphere causes reactions between the methane and nitrogen to form reactive nitriles. And these are the first step towards building nucleobases, the building blocks of RNA. The model suggests that this altered state lasted for millions of years, long enough for organic molecules to proliferate and seed the surface of the Earth. But that hydrogen gas was light, so light that Earth's gravity wasn't strong enough to hold onto it forever. It slowly escaped into space, and eventually losing this hydrogen brought the reducing atmosphere to an end. Until the next major impact, that is. Looking at the pattern of craters on the Moon, it's likely this sequence of events happened as many as 7 times during the Hadean. And while each impact was big, they probably weren't big enough to reset things back to square one. We think this because a 2009 study used a computer model to simulate asteroids hitting the early Earth and found they probably wouldn't have sterilized the planet like that big Theia collision that formed the Moon. So they seem to have provided the conditions for life without wiping the slate clean. Maybe then, life didn't arise in spite of the constant bombardment of asteroids, but because of it. And there's a growing body of research that's beginning to reveal just how these impacts from outer space were crucial to the origins of life. For example, a 2015 experiment showed the plasma created during the smaller asteroid impacts can turn the simple organic molecule formamide into the nucleobases used in RNA. And in 2023, scientists analyzed samples taken from an asteroid by a spacecraft and found amino acids as well as one of the nucleobases used in RNA on the asteroid. So they could have even brought some of these to Earth directly. Comets crashing into Earth might be part of the story too. When they hit, the ice in them receives a sudden shock wave of pressure. And lab experiments have found that this can link amino acids together to make peptides, which is another step towards making proteins. So while we don't know exactly what caused the right conditions for the building blocks of life to form, We know they did. After all, we do exist. And it's becoming increasingly likely that even though these impacts at one point rendered the Earth uninhabitable, at the end of the day, they are precisely what made it ultimately habitable. Life, that thing that Earth is uniquely famous for, may have only happened because of rocks from space.
Did you know the team that makes this show also makes another show about the strange creatures that inhabit the Earth? Except this time, all of the creatures are very much alive, and we have video of them to prove it. Join Hank Green and Sarah Suda as they introduce you to these bizarre beasts and explore what makes these animals so weird to us. From bats that can fish to worms with hundreds of autonomous butts, the show examines the how and why of some of the world's most amazingly strange creatures. Check out Bizarre Beasts in the link in the description.
So, space rocks may have helped life get started on Earth, but what was it like? Find out in our episode, The Search for the Earliest Life. We gotta thank this month's impactful eontologists:
Addie, Annie, and Eric Higgins, Carl Wolfel, Jake Hart, John Davison-Ng, Juan M., Melanie Lamb-Carnevale, Nico Robin, and Raphael Hasse.
By becoming an Eonite at patreon.com/eons, you can get fun perks like access to behind-the-scenes content, including clips from Eon shoots. And as always, thanks for joining me in the Ken Barnes studio. Subscribe at youtube.com/eons for more happenings in the Hadean. Subscribe at youtube.com/eons for more happenings in the Eon. No. So close. Okay.